Good afternoon, everybody, and welcome to this STEAM webinar for EduCaixa Talks. We have the stellar presence of James Tanton here. He's the creator of Exploding Dots and the promoter of the Global Math Project, a global program followed by math schools at all kinds of levels. But before we start, I would like to thank Sergio Belmonte and Fernando Blasco. Sergio is a high school teacher and the vice chair of the Catalan Museum of Math, and he was the first person to tell me about James, and who told me, "Oh, you have to meet James and find out about exploding dots." I'm really grateful to him for it. Fernando Blasco, on the other hand, teaches at the Polytechnic University of Madrid. By the way, that university will be teaching a degree in math starting next year. And, Fernando is involved in the Hello Math program in EduCaixa. Sergio will be joining us today in a while. He'll be illustrating classroom practices using exploding dots. And Fernando, who's also hovering around here, was kind enough to put us in touch with Carmen Casares, who's also a high school teacher, who will tell us how exploding dots can fit into the high school math curriculum. Without them, we wouldn't be able to be here, especially in the way that we're going to be here together. The Catalan Museum of Math and the Spanish Association for Math, where Fernando Blasco is the chair of the dissemination committee. These are the two collaborating institutions in this webinar. I hope and trust that we will continue to collaborate in the future, also on exploding dots with James Tanton. I think there's no need to explain why we've asked James Tanton to talk about exploding dots at this point. Exploding dots is a representation system that really conveys the essence and behavior of numbers, and numbers are the structure of math. Numeracy is the basis of mathematical knowledge, so a representation system that's rich, powerful, and surprising, like exploding dots, guarantees successful learning of math. So the reason we have James Tanton here is because exploding dots is simply wonderful, as you will see. But in addition to this, just as a bonus content, in the context of Hello Math, which is an integration of math and computing, computing as, finding out how you have to get what you want from a computer. We have to learn about the ways humans think, the ways computers think, and how they're similar and how they're different. And exploding dots is really helpful in terms of helping see how humans represent and process numbers and how computers do that. So without much further ado, I'll hand over to James Tanton. So presenting James Tanton, the floor is yours.
Oh my
Thank you very much for being here.
Oh, an absolute honor and a pleasure to be here. Thank you. Hello, Europe. I'm based in Phoenix, Arizona right now, and I'm just wish my physical presence was there. I'd love to see you all in person, be here virtually. So thank you so much for having me on today to share this incredible story of the joy of mathematics. I so appreciate it. I'm so truly honored. But before I begin, I have to ask a very important question. Is everyone, are all my friends in that part of Europe aware that there is an international salute to mathematics? Did you know there was a math salute to the joy of mathematics? Okay, I can't quite see you right now, but I suspect some people are doing this. I don't know there's a math salute. So before I begin, let me teach you the international salute to mathematics. It goes as follows. Try it with me. All right. Unfortunately, you need your arms free, so you have to put down anything you might be snacking on, or put down all your drinks and so forth. It begins as follows, arms free. And what you do is you put your arms straight out in front, which is good. Great. Then you go right hand over left hand. That's the hard part, right over left. All right, when we're there, next you go palm to palm. And then the salute gets strange. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, just come on back. Whoa, 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 how did that happen? Whoa, maybe I should do it again. Maybe I should do it again. I'll try from a different angle, see if this helps. See if I can do it sideways for you. Okay, arms out front. Yep, I'm on the camera. There we go, on the camera. Arms out front, right hand over left hand. So you see I'm not cheating. It really is my right hand over my left hand. Palm to palm. Wiggle the little fingers. Wiggle the thumbs. Wiggle the little fingers again. And then when you're ready, just come on back. Whoa, whoa. Now, I'm not making this up. This really is an international salute to mathematics. So if you Google International Math Salute, you will find this. But here's the deal. I'm very happy to explain how it works and give the secrets away. So when we come to our question and answer session, feel free to ask me, James, how do you do the International Salute to Mathematics? And I'll give it away for you. I'm in a good mood tonight. I'm feeling very happy to be here. I'll give away all my secrets, including the secrets of exploding dots. So let's get cracking. Let's talk about those fabulous exploding dots. And to do that, I'm going to share my screen. And this has really become quite a phenomenon. This has become a worldwide phenomenon. As Marta was pointing out, it really is about the essence of mathematics. In fact, it really is about how we think about and write numbers, the story of place value in mathematics. And I have to say, I think the invention of place value is one of humankind's greatest intellectual achievements. And it really permeates every aspect of mathematics. All the early mathematics we do with our young students, all of elementary mathematics, all of middle school mathematics, all of high school mathematics. I actually left the university world and became a high school teacher for 10 years because the depth of the mathematics there is profound. And it goes to university level mathematics and beyond. The story of place value permeates all of mathematics. And I want to give you a good taste of this wonderful story of exploding dots today. So here it is, exploding dots. And this really is a worldwide phenomenon at this part. So I'm so excited to share this in Spain and Catalonia. This is going to be great. Here's a young student in Tanzania, in Africa, doing exploding dots. So let me start the wonderful story of exploding dots with you tonight. I am so excited. Let's get going. The story of exploding dots all begins with a tale, with another story that's not true. Here it is. Here's my story that's not true. When I was a young child, I invented a machine. Not true. And all the machine is a row of boxes that go as far to the left as I desire. As many boxes to the left. If I want 5 boxes, 5 is good. If I want 7 boxes, 7 is good. If I want 100 boxes, 100 boxes is good. Any number of boxes you like. They go as far to the left as you desire. And in this untrue story, I gave this machine a strange name. I called it a 2-1 machine, but in a funny backwards way. I mean, I am a young child in this story. I knew no better. Writing it backwards seemed fine to me. But I even say 2-1 machine. And here's how the machine works. What you do is you put in dots. And if you've got 1 dot, dots will always go into the rightmost box. So here comes a dot. Zoom. Now, I hope the interpreters are making sound effects. I made the zoom sound, so I hope the interpreter is making zoom as well. Good luck. Have fun with that. All right, but 1 dot in a box. Well, not very exciting. It just stays as 1 dot. However, bring a 2nd dot into the machine, always into the rightmost box. Zoom. Okay, there's 2 dots in a box, because then something exciting happens. Whenever there are 2 dots in a box, kapow, they disappear and become 1 dot, 1 place to the left. 2 dots became 1, hence the name 2-1 machine. 2 dots explode away and become 1. Kaboom. All right, okay, so now 2 has no dots, no dots, no dots, no dots, and I'm going to write 1 dot, 0 dot. 1, 0 as the code for the number 2 in this 2-1 machine. Very interesting. But let's keep going. Here comes a 3rd dot. A 3rd dot, always into the rightmost box. Zoom. All right. Well, no explosions now. I guess the code for 3 is 1, 1. All right. Here comes a 4th dot. I have a feeling putting in a 4th dot is going to be particularly exciting. Here it comes, always the rightmost box. Zoom. Okay. Oh, 2 dots in a box. Kapow! They disappear and explode to become 1 dot, 1 place to the left. But then 2 dots in a box. Kaboom! 1 dot, 1 place to the left. Wow, wow. So the code for 4 is nothing, 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 1 dot, 0 dots, 0 dots. I'm going to write 1, 0, 0. Now, can you see what the code for 5 is going to be? Always put dots in the rightmost box. Zoom. Yeah, 1, 0, 1. Can you see what the code for 6 is going to be? Now, I don't know if we have chat capabilities, but maybe we can. Type into the chat what you think the code for 6 is going to be. Can you guess what it's going to be? Let's see, does chat work for us today? Maybe not, maybe not. Okay, but I have a feeling if I put in the 6th dot, here it comes. Zoom. There's the 6th dot. Oh, but there's 2 dots in a box. Kapow! 6 is 1, 1, 0. Hours of fun to be working out different codes. In fact, I could work out the code for 7 and 8 and 9 and 10 and 11 and 12 and 13. But I can go really high. But actually, let me do 13. I'll do the code for 13. Why not? I'm going to put in 13 dots in the machine. Here goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 dots. Oh, but there's going to be explosions. Kapow! Dot. Kaboom! Dot. Kajing! Dot. Kafling! Dot. Kafloom! Dot. Kablip! Dot. Whoa, lots of dots there. But more explosions, more explosions. Kajubal! Dot. Kaflimble! Dot. Kaflingle! Dot. But then more explosions. Kafimble! Dot. I think that's it. 1 dot there, 1 dot there, no dots there, 1 dot there. Oh, it looks like 13 is 1 dot, 1 dot, 0 dots, 1 dot. Wow, wow. And for those that were listening to Martin and have to know some computer science, you might know what's secretly going on here. You might be able to guess what this machine is actually doing. But remember, in this story, I'm still a young child. I don't know what this machine is doing. They're just giving me strange codes for numbers. But then, one day in this untrue story, I had a flash of insight. I realized instead of doing a 2-1 machine, I could do instead a 3-1 machine. Why not? 3-1. Whoa. Now, 3 dots need to explode. 3 become 1. Okay, let's try it. Let's put in some dots. Put in 1 dot. Zoom. Just stays as 1 dot. Not very exciting. Put in a 2nd dot. Here it comes. Zoom. Oh, just stays as 2 dots. Not very exciting. You need 3 dots to explode to become 1. So it's still just 2 dots. 2 dots is it. Here comes a 3rd dot. Always the rightmost box. Zoom. Now 3 dots. 3 dots explode. Kaboom! Become 1 dot, 1 place left. 3 become 1. So the code for 3 is nothing, 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 1 dot, 0 dot, 1 dot, 0 dot. Here's the code for 4. Zoom. 1, 1. Here's the code for 5. Always the rightmost box. Zoom. Oh, not very exciting. 1, 2. Here's the code for 6. Here it comes. Zoom. Oh, 3 dots. Kapow! Dot. 2, 0, and so on. Hours of fun working out codes in a 2-1 machine. In fact, why don't I do 13 again? This is kind of fun. I'll do 13. That was cool last time. Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, here goes. 3 dots explode. Kaboom! Dot. Kaboom! Dot. Kading! Dot. Kafloom! Dot. Okay. Oh, 3 dots. Kabooms! Dot. Looks like I've got 1 dot, 1 dot, 1 dot, 1, 1, 1. Nothing, nothing, 1, 1, 1. Beautiful. There's the code for 13. Hours of fun. Hours of fun to be had. Gotta love it. Gotta love it. But then I had another flash of insight. Instead of doing a 3-1 machine, I could do a 4-1 machine. Or I could do a 5-1 machine. Or so on and so on and so on. So let's get crazy. Let's go crazy right now. Let's do all the way up to a 10-1 machine. Whoa. 10-1 machine. That's insane. In fact, let me be really insane-er, crazier. Let's put 273 dots in a 10-1 machine. Whoa, whoa. What is the secret code for the number 273 in a 10-1 machine? All right. So unfortunately, I can't see you, so I don't know what your face is looking like right now, but maybe you've got an idea what's going to happen. Now, I'm a fellow of little brains. I'm going to actually truly do this. We've got plenty of time together. I'm going to put in 273 dots and really do it. I'm a slow thinker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I don't know how the interpreters are going to interpret. I hope they're having a good time interpreting these sound effects. Do you think I'm at 273 yet? Is that 273 dots? Guess you're not going to make me stop, because no one can make me stop until I think it's 273. Right, 273, done. We'll say it's 273 dots. All right, so to show you how my simple brain works, I'm going to ask a basic question. Will there be any explosions? Yes or no? And yes, there's going to be lots of explosions. There will be explosions. In fact, every 10 dots will explode. 10 dots will explode. 10 dots will explode. 10 dots will explode. There'll be lots of explosions. In fact, let's ask that. How many explosions will there be? Well, there's 273 dots. 1, 2, 3, 4. I guess it's going to be what? 27 groups of 10? Groups of 10? I think that's right. So, kaboom dot, kabing dot, kajoom dot, explode, explode, explode. I guess I'm going to have 27 explosions, makes 27 dots there. And that will leave, I think, 3 dots left behind. 1, 2, 3 dots get left behind. So explode, 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 explode. All goes away. Got 3 dots left behind. 3 dots left behind. Okay. I'm still hanging on there. That's good. I understand that. But now I think there's going to be more explosions. In fact, 2 more explosions. Kaboom, kapow, dot, dot. And leaving what, 7 behind? 1, 2, 3, 4, 5, 6, 7. Oh, I think that does it. And I think what people were saying on the chat, my fellow panelists are saying, they were saying 273 is the code. And do you know what? I'm seeing it. 2 dots, 7 dots, 3 dots. Yes, the secret code to the number 273 in a 10-1 machine is 273. Whoa, whoa. Now, I'm sure you're probably onto me. You probably figured out what these machines might really be doing, but this is a big moment right now because we've discovered something profound. In fact, let's see if we can figure out and explain for sure, for real, what these machines really are doing. So let me go back to the beginning. Let me go back to, say, the 2-1 machine. Now, what was this game? What's this thing I'm doing? Well, we played this game where dots would always go in the rightmost box. If I put a dot there, it's worth 1 dot. That was 1 dot. But the thing is, if I put 2 dots in that machine, that's a 1 and a 1. These 2 1s, kaboom, make a dot there. So this dot here is worth 2 of those. It's worth 2 1s. It must be worth 2 1s is 2. And also in this 2-1 machine, if I had 2 dots there, you know what's going to happen. They'll explode. These 2 2s, kaboom, make 1 dot there. So this dot here must be worth 2 2s. It must be worth 4. And 2 of these, kaboom, make 1 of those. This must be worth 2 4s. That's 8. And 2 of these, kaboom, make 1 of those. This must be worth 2 8s, which is 16. If I kept going with more boxes, then 32. Keep going with more boxes, double that is 64, and double that's 128, and then 256, and then 512, and then I'm stuck. That's enough. That's enough. Beautiful. But here's the lovely thing. Here's the lovely thing. We said 13 was 1101. We said 1 dot there, 1 dot there, 0 dots there, and 1 dot there. Can you now see, and I mean literally see, that that is the correct code for 13. It's 1 of these, it's 1 of these, none of those, but 1 of those. And you realize, yes, I can see that really is 13. 1 8 and 1 4 and 1 1 really do make 13. Wow. Welcome to base 2. Welcome to what people call binary. Here's the words people use for this. We are writing all the numbers in base 2. We only ever use the digits 1 and 0s. And this is why computers love base 2. Because computers are based on electrical switches. And these switches can either be on or off. That's it, on or off. That's all computers have, little switches are either on or off. And they often use the symbol 1 to mean on and 0 to mean off. So here's a way to write all of mathematics in electrical switches. Example 13, I can do it in 5 switches. We said 13 was 1, 1, 0, 0, 0, 1. So I don't need the first one. There's a 1, on. There's a 1, on. Keep that one off, next one on. There's the number 13 in binary. In fact, it's literally this. I'm doing it. 1, 8, 1, 4, don't use the 2, and 1, 1. There's 13 in binary. Here's the number 31 in binary. Whoop. Here's the number 5 in binary. Whoop, whoop. A 4 and a 1 makes 5. This is exactly how computers do mathematics. In fact, this is how your smartphone is doing all its mathematics. Everything is in base 2, binary. All right, well, that's great. So what about the 3-1 machine? How did that one work? I guess it'd be the same idea. Dots here are worth 1. I set the game up so dots there are always worth 1. But now 3 of these make one of those. Kaboom! So that must be worth 3 1s. Must be worth 3. And 3 of these, kaboom, made one of those. So this must be worth 3 3s, which is 9. And 3 of these makes one of those, 27. And 3 of these makes one of those, 81. And 3 of these makes one of those, 243, and so on, and so on, and so on. And check, 13. We said it was 1, 1, 1. I bet you can now see this is right. Can you see that 13 is indeed one of those, one of those, and one of those? 1, 9, and 1, 3, and 1, 1 is indeed 13. Beautiful. Welcome to base 3. Wow, we're writing all our numbers now in 3 symbols, in 1s, 2s, and 0s. You can write all your numbers in 3 symbols. And that makes me think I now know what's going on with the 10-1 machine. It must be exactly the same. That dots there in the rightmost box. Here's one, sorry, fumbling. There's one, are worth 1. 10 of these makes one of those. 10 1s is 10. 10 of these makes one of those. 10 10s is 100. 10 of these makes one of those. 10 hundreds is 1,000, and so on, and so on, and so on. And there is our code for 273. It is literally 2 of these, 200s. It is literally 7 of these, 7 10s, and 3 of these, 3 1s. In fact, in English, at the very least, we literally say that. We literally say in English, 273. 200s. Yes, we literally say 200s. There they are. 7T. English is a bit weird. TY is short for 10 in English. There's 7 10s and 3. So in English, we speak base 10. So I'm curious. I don't know my Spanish. Does Spanish speak base 10 as well? Do you say 273 in the same way in Spanish? Okay, so you're also using base 10. What about Catalan? Does Catalan also use base 10 and how it says its numbers?
Sí.
Okay, interesting. You wonder if every language uses base 10. In fact, that begs the question, why do we humans like the number 10 on matters of arithmetic and counting? What drew us as human beings to thinking about 10s as the way to go for counting? You think about it for a while, like you scratch your chin and say, humans, why do humans like the number 10 so much? And then you realize, oh, because we're born with these things. We've got 10 digits on the end of our hands. We think 10 is a very good number for counting because we do it all the time with our fingers. Wow. Computers only have switches that are on or off. That's why 2 is very good for computers. You only got 2 fingers, if you like, an on and off. But we humans are naturally born with 10. We think 10 is a good number for counting. Therefore, we went base 10. Welcome to base 10. Though, I should point out, our culture goes base 10. Some cultures went base 20. 20. Why did some cultures on Earth go base 20? Any thoughts? And you think about that for a while, say base 20, who's thinking base 20? And you realize, oh, they must be thinking of their fingers and their toes. If you look down, you've got fingers and toes to count on. So these people are probably thinking fingers and toes. Interesting. And by the way, we have little vestiges of base 20 still left to this day in our Western world. For example, I want to know your neighbors, those in France, say 87 in a very strange way. How do you say 87 in French? Now, I don't speak Spanish, I don't speak Catalan, and I don't speak French, so I'm in trouble today. How do you say 87 in French? If you think about it, it's very strange. I believe it's 80. I really don't speak French, forgive me. Set. Is that right? They are literally saying 4 20s and 7. That's 87. They're speaking base 20. 4 groups of 20 plus an extra 7. Whoa. Yes, a little bit of base 20 in French to this day. Oh, I should point out, some cultures on this earth went base 12. Base 12? Where did 12 come from? Why base 12? Okay, so you think about this for a while, and actually, so Portuguese uses base 10 for their numbers. This is interesting. Actually, this is a great opportunity to chat with your students who come from different parts of the world. The number systems they know in other languages, do they use base 10? Do they use some base 20? They might even use some base 12. It's actually very interesting. Great discussions we had with anyone you're talking to. This is great, fascinating. Okay, but there is a reason for base 12. There are some cultures that to this day have realized there's a very good way to count to 12 on one hand. That you'll see this in many parts of India and Southeast Asia to this day. People notice we have 4 very long fingers naturally divided into 3 sections. There's 4 long fingers and 3 sections with this very handy pointer, this thumb, a very handy pointer. And you'll see people count like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Some people really do count to 12 this way to this day. In fact, some of your students in your classroom, you might see them counting like this. It's very popular in many parts of the world. In fact, I just did 1 group of 12. In fact, I just did 2 groups of 12 just then. I did a 3rd group of 12. There's a 3rd group of 12. In fact, I could do 12 groups of 12 on my 2 hands. I can count 144 on my 2 hands this way. Whoa, that goes way beyond 10. We get to 144. Gotta love it. And we actually still see lots of 12-ness in everyday life. I mean, I'm living in America. They use feet and inches. How many inches are in a foot? Well, it's 12. How many items in a dozen? Well, it's 12. How many hours are in a day? My hours in a day? Oh, actually, there's a trick question. How many hours are in a day? Careful, I mean literally a day. So this goes back to ancient times. You ask yourself, okay, measuring time. The first way humans measured time was basically with a stick in the ground. They put a stick in the ground or on a disc or something, and they just looked at the shadow from the sun. They actually invented sundials. The first clocks were sundials, and they noticed that the shadow, as the sun moves around, actually goes around on the circle. And that's why people actually started associating time with this direction from shadows on a sundial. And when they started measuring time, they said, well, let's divide the hours of the day into 12. They chose 12 hours in a day. And then eventually humans invented water clocks and mechanical clocks and so forth. They could start measuring time at night. They said, oh, well, we're doing 12 hours in a day. We might as well do 12 hours in a night as well. So we today say there's 24 hours in a day, but it really came from the number 12 in literally a day. Because you can only use sundials during daylight. They don't work at night. So people never bothered measuring time at night. They just did hours in the day, which is really interesting. So we still have some 12-ness to our days, to our number system. I love it, absolutely love it. All right, but let's go back to school mathematics. This is the human story. Actually, I love the human story. Math is full of human stories. Let's make mathematics a human experience for our fabulous young humans, is what I say. All right, here goes. Let's start going through all of school mathematics. We have 30 minutes left together, or 25 minutes left together. Let's do all of it. Let's do all of it. So we've just learned how we write numbers. I will stay in base 10 because most people want us to stay in base 10, though I'm sure we could do this in base 20 or base 2 or base 12, whatever base we like, we could do it. But I'll use a 10-1 machine. And one of the first things you learn in math class is a long addition, apart from just the very basic familiarity numbers. For example, I'm going to do 413 plus 124. And I'm sure that one is very straightforward. I bet everyone's thinking 4 plus 1 is 5, 1 plus 2 is 3, 3 plus 4 is 7. I bet it's 537. Now, if you're watching me, you may have noticed I did something very strange then. If you were very observant, you may have noticed I started at the left and went to the right. I started left to right. And here's a true part of the story. I was very confused as a young kid in class, as I was being taught to read English, at least, left to right. Every class was going left to right. Be my English class, my writing class, my social studies class, my art class, everyone was left to right, except maths says, no, James, you must go right to left in math class. And I went, huh? I thought that was weird. I thought that was very weird. And look, if I go right to left, 3 plus 4 is 7, 1 plus 2 is 3, 4 plus 1 is 5. You get the same answer. So why does it matter? Why does it matter? So I was very confused as a young kid. All right, but let's see. I know what you're thinking. I know what the audience is thinking right now. That was too easy. That was too nice a problem. Let me do a more complicated problem, like 478 plus 143. How's that one? Okay, well, I'm going to go left to right. 4 plus 1 is 5. 7 plus 4 is 11. 8 plus 3 is 11. The answer is 511. 11. Whoa. 511. But I'm going to show you I'm absolutely correct. Because here's what the problem is as a picture. In the 10-1 machine, I've got 478. 400s, literally. 70, 7 tens. Here they are. And 8 ones. There's 478. I'm being asked to add 1 more 100. Okay, 1 more 100. I'm being asked to add 4 more 10s. No worries, 4 more 10s. Please add 3 more 1s. Okay, 3 more 1s. And all I have to do is ask myself, well, how many 100s do I have? I have 5 100s. How many 10s do I have? I see I have 11 10s. And I see I have 11 1s. The answer really is 500, yes. 11T, yes. 11, yes. 511. You know what? I am actually a professional mathematician. You might not realize it, but what brought me to America 35 years ago was to get my PhD in mathematics. I have a doctorate in mathematics. I am a doctor of mathematics, and I give my official stamp of approval to that answer. There's nothing mathematically wrong with that answer. 511 is absolutely correct. Mathematically solid. It's just that society thinks this sounds weird. Society says, James, you can't say 11T, don't be silly. And then they say, James, you can't say and 11, don't be silly. Okay, just for the sake of society, not because of maths, just for the sake of society, we can fix this answer up to make society happy. Here's what I'm going to do. I'm going to explode 10, because this is a 10-1 machine, remember. 10 explode, kaboom! Leaving what, 1 behind? So 1 gets left behind, and an extra dot there, and I guess that makes 6. The answer is 611. That is still correct. There's nothing mathematically wrong. That's a good, solid answer mathematically, just that society still thinks that's weird. Okay, so they might want me to explode again. I'll explode again. Kaboom! I guess 10 explode, leaving 1 behind, making an extra dot there. So I guess the answer is 621. 621. Okay, society is happy, but there it is. This is long addition. I say just go left to right, like you're taught to read, at least in our Western world, and everything makes perfectly good sense. By the way, here's what I was taught as a student. 478 plus 143 I was to go right to left as I was taught, I'd say 8 plus 3. I want to write 11. I was not allowed to write 11. James, you don't write 11. So what you do is you explode 10 away, leave 1 behind, and put an extra dot up there. Kaboom. It's the same. It's the same. And I'll do it again. 1 plus 7 plus 4. I want to write 12. But I was taught, no, no, no. 10 explode. Kaboom. Boom. Leaves 2 behind, an extra dot there. 6. So actually what I was taught in school is the same as what I'm doing now. But I understand this. I feel like I understand. Just go left to right and do all the explosions at the end. School has you go right to left and do all the explosions as you go along. Okay, okay. But let's keep going. For example, what if I did multiplication? 2, 7, 8, 4 times 3. What would be the James Tanton answer, do you think, to that problem? Can you write in chat, and then my fellow panelists will tell me what people are saying. What do you think James Tanton will give us the answer to that one? James doesn't worry about what society thinks. What do you think James Tanton would give us the answer? Here it is at a 10-1 machine. 2, 7, 8, 4. Nothing yet. Okay, okay. Well, James Tanton could tell you James Tanton's answer, because I've got an answer in my head right now. What I'm really being asked to do is take this number, 2 thousands, 7 hundreds, 8 tens, and 4 ones, and just triple everything. I bet the answer is 6, 21, 24, 12. Because if you think about it, just common sense, common sense. If I've got 2 thousands, I say triple them, I guess that makes 6 thousands. I've got 7 hundreds, and I say triple them, I guess that makes 21 hundreds. I've got 8 tens, I say triple them, I guess that makes 24 tens. Common sense. 4 ones, tripled, makes 12 ones. Done. The answer is 6,000, 2100, 24 T 12. Whoa, whoa, whoa. Okay. Again, it is true. I am a doctor of mathematics. Yes, there's my stamp of approval. Thumbs up. There's nothing wrong with that answer. That's mathematically fine. It's just that society does not like that answer. So what could we do to fix up that answer for society's sake? Okay, try it. How would you convert that to one that society would like? Can you do it? Yes, of course we want to explode them. Who doesn't want to explode them? Let's explode them. Example here, kaboom, kapow. Leave 1 behind, make extra 2 dots there. So there's 8, 1, 24, 12. Okay. Oh, 10 could explode here, kaboom. Leave 2 behind, an extra dot there. So that's 8, 1, 25, 2. Oh, kaboom, kapow. Leave 5 behind, 2 dots there. 8, 3, 5, 2. I think society likes that answer. There it is. Lots of fun. Oh, actually, while I'm here, here's something that's very confusing for students. Very confusing for students. Suppose we were doing something like 243 times 10. When I was in school, I was told to multiply by 10, just add 0. To multiply by 10, just add 0. Here's what I said. Huh? That made no sense to me as a kid. 243 plus 0 is 243. Weird. Just add 0? They don't mean that. They mean something else. Surely they mean something else. And of course, I know what they mean to say. They say 2, 4, 3, just add a 0 to the end. Just add a 0 to the end. But here's my question. Why? Why does that work? I was just told to do that, and I did it. I obeyed. Let's think about it. Let's think about it. Let's go to a 10-1 machine. Here's lots of boxes. 200, 4 10s, and 3. Please multiply everything by 10. Okay, I'll have, instead of 200s, and I'll have 20 hundreds. Instead of having 4 10s, I'll now have 40 10s. Instead of having 3 1s, I'll now have 30 1s. But then look what happens. Look what happens. Kaboom, kapow, dot, dot. Kaboom, kapow, kazing, kazoop, dot, 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 dot. Kazing, kazoop, zoop. 3 explosions, 3. And look what's revealed. I get 2, 4, 3, and no dots. So what's really happening, I'm not really adding a 0. I'm really, in some sense, all the digits shifted over and I revealed a 0. A 0 at the end was revealed. Now I can understand why that works. Now I'm happy to do that. Yes, I'll put a 0 at the end now that I understand why it works. This is the beautiful thing about really thinking deeply about place value. All these mysteries come into place. In fact, while we're at it, let's have some fun. Let's try this. Here's a very easy multiplication problem. I know we all know the answer. The answer is 3906. But let me really spend some time on this. Let me really focus on this. Because what I'm really asking you to do is the following. Please take this number, 1,000, 300s, no 10s, and 2. And I'm being asked to triple them, triple everything. I'm going to literally triple everything. Here's how I'm going to literally triple it. That 1 dot now becomes tripled. It's now 3 dots. This 1 dot is now tripled. It becomes 3 dots. We'll make it look like a dot. There we go. This dot gets tripled. Make it look like 3. Now make it 3 dots. This dot gets tripled. Now it's 3 dots. This dot gets tripled. Now it's 3 dots. This dot gets tripled. Now it's 3 dots. Beautiful. And now I am seeing 3906. 3906. Beautiful. Beautiful. Great. All right, so far that was multiplication. But let's go backwards. Let's start doing division. We've got good 15 minutes left together. Let's do division. So pretend you didn't know that. Pretend you never saw that. Suppose I asked for 3906 divided by 3. What I'm asking for now is, here's a picture of 3906. How many 3s do you see in it? What got multiplied by 3 to give the answer 3906? What got multiplied by 3 to give me 3906? And you say, okay, I can do this, because I look at the picture and say, oh, there's a dot that got tripled. So there's a dot there that got tripled. Oh, there's a dot here that got tripled. Oh, there's a dot here that got tripled. Oh, there's a dot here that got tripled. Nothing got tripled there, but there's a dot there that got tripled, and there's a dot there that got tripled. So I guess, oh, I can see what's going on. What actually happened here, it must have been 1 dot there in the thousands place, 3 dots there in the hundreds place, no dots there in the tens place, and 2 dots there got tripled. It was 1302 that got tripled to give me 3906. I found all those groups of 3 in 3906. We are now doing division. We're now doing division. In fact, I'll pause for a moment. Can you, on a piece of paper right now, just draw me a dots and boxes picture of 426 divided by 2? I know the answer is 213, but can you see it in a dots and boxes picture just for yourself? Actually see it. What would the picture look like? Give it a try. Yeah, I think you're on it. Also, when we're doing equal signs, so this is 426 divided by 2. You say, well, what got doubled? And you see lots of things got doubled. That got doubled, that got doubled. There's a dot doubled. Here's a dot doubled. There's another dot doubled. There's another dot doubled. Yes, I really am seeing 213. There must be 213 groups of 2 in that picture. In fact, there are 2 at the hundreds level, 1 at the tens level, 3 at the units level. we have 213. Whoa, this is gorgeous. In fact, let's do another one, because there can be little bits of trickiness. For example, try this one, 416 divided by 4. Now, I know the answer is meant to be, what, 104? So we know what the answer is, but the question is, can you draw a picture of it and see what slight snag there might be? What little complication could there be? It's a lovely learning moment for students to have these little complications. There's a group of 4. Here's a group of 4. Here's a dot that got quadrupled. And then I get nervous because I'm feeling stuck right now. I know it's 104, but I'm not seeing it. I'm just not seeing it. What could I do? Oh, my method, my beautiful method is failing. My beautiful method is falling apart. What can I do? Oh, we are stuck. Right now I've got 101 with like a 10 and 2, like 12 dots left over. Can we unexplode? Someone said on a chat somewhere, it just communicated to me, can we unexplode? Well, the answer is, well, yeah, if you want to unexplode, yes. The answer is always yes. Which case, I think I know what you mean. This little dot here must have been 10 dots over here that went kaboom and spilled over. So I might want to unexplode that. Bring this back to being 10 dots. Unexplode. So let me do a sound effect like, let's do a sucking sound. Unexploding is a sucking sound. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's unexplode it. Oh, I love it. Unexplode. Brilliant. Brilliant, I say. Good job. You are being such mathematicians, because now I find more groups of 4. There's a dot that got quadrupled. There's a dot that got quadrupled. There's a dot that got quadrupled. Absolutely brilliant. And yes, it's 104. So exciting. So exciting. Brilliant. So that little complication, we figured out a way around it. Let students own those moments. Let the class be stuck on those very moments. They are beautiful moments to push your way through. Gotta love it. You've gotta love it. All right, but that's single digit division. Let's go up a notch. You are ready to keep going. Let's try something like 276 divided by 12. All right, now I'm going to be honest. If I truly want the answer to that problem, I am a citizen of the 21st century and I'm going to do this. That's what I would use. I'm actually going to try to do this problem. So let's see if I can actually see what the answer is. 276 divided by 12 is 23. I'm done. My work is done for the day. It's 23. So here's a strange thing. We often teach classes as though students aren't citizens of the 21st century. We forget they have technology. So we can't be teaching this stuff for the sake of getting answers. This is the smart way to get answers. So we have to be teaching about the thinking, about this human story here. So let's see if I can think my way through this one, because it's actually really fascinating. Here's 276. Here's the thinking that's fun and good. 276. And I'm looking for 12. And what does 12 look like? Well, 12 is 12 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 dots all in the box. But we've learned today already that society is demanding. It says, James, you can't put 12 items at a place value. You must explode. You must explode. 10 explode, make 1 dot there and 2 dots there. Please write 12 as 1, 2. But here's the thing. That is annoying. All 12 dots really were there, really were in this rightmost box. Oh, my camera's frozen. Come on, camera, come on, camera. Yeah. All 12 dots really were right there, but they went kaboom and spilled over. So 12 dots are really in the rightmost box. So 12 looks like one dot next to two dots. So the question is, how many 12s do you see in 276? How many one dot next to two dots do you see in this picture of 276? You stare at it for a while, and I wish we had direct communication, because I bet you're seeing some one dots next to two dots right now. You might be seeing like this. There's one dot next to two dots, right there. That represents 12 dots. And where are the 12 dots really? Well, they must all be there. All 12 dots there, and kaboom, they spilled over. So actually all 12 dots are right at that level. Okay, any other 12 dots in this picture? And you look at this and say, oh, right there's another one dot next to two dots. And where are the 12 dots? Oh, they must all have been there in the right part of the loop, but kaboom, spilled over. So they're all right there, again, at that level. And the other 12 dots in this picture, you look at this and say, oh, yes, over here. There's one dot next to two dots, but they must be over here in this right part of the loop. All 12 dots must have been there, and kaboom, spilled over. So they must all be there. And look, I see another 12. I am so excited. Oh. And I see another 12. Oh, I love it. I love it. And yes, 2 at the tens level, 3 at the ones level. The answer truly is 23. Wow. Wow. I love it. I love it. Okay, your turn. On your own. Draw me a picture for 2784 divided by 23. Draw me a dots and boxes picture of that one. Can you do it? The answer is yes, I know you can. Give it a try and see what happens. Are there any problems? My camera's out of focus. There we go. Come on, camera. Be back in focus. But I'll draw it so my camera focuses. All right, all right. We're looking for 2 dots next to 3 dots. If I just want the answer, here's what any intelligent person would actually do. 2784 divided by 23 equals 121. 121 and stuff. This one's confusing. This one is confusing. Well, let's do it. Let's do it. 23, 2 dots next to 3 dots. 2 dots next to 3 dots. There's 23. And where are all 23 dots? They must have all been there, and kaboom, kapow, and spilled over. Here's 2 dots next to 3 dots. Whoa, right there, another 23. They must have all been there, kaboom, kapow, and spilled over. In fact, there's another 2 dots next to 3 dots right there. Love it. In fact, I can do it again. 2 dots next to 3 dots right there. Yes, I do see 121 plus, one extra dot. Now, depending on where you are in the world, if you're in primary school, people will say plus remainder 1, a remainder of 1. Maybe people say that sort of thing. Or if you want the actual math answer is plus 1 more dot, still waiting to be divided by 23. Please divide it by 23. So it's really 121 plus a remainder of 1, or 1/23, however you want to do it. Beautiful. You'll see remainders. All right, I have 3 minutes left. And in 3 minutes, I want to explain to you why, when I left the university world to become a high school teacher, I did everything I did to you right today with my students, my high school students, because I had to teach high school mathematics, and we are ready right now to leap from grades 4, 5, what a year level this is, to high school math. I'm going to do it. The point is, math does not care about us being human. It doesn't care that we have 10 fingers. If we're a Martian, we only have 6 fingers. Martians have 6 fingers. They'll do a 6-1 machine. They'll do everything in base 6. People on Venus have 8 fingers. They'll do everything in 8-1 machine. So what I'm going to do now is I'm going to do it in all machines all at once. Whoa, whoa, all machines all at once. That is, it could be a 10-1 machine. I'm not going to tell you. It could be a 6-1 machine. I won't tell you. It could be a 3-1 machine. I won't tell you. But if there's a number that's in my head, I'm not telling you. For some reason, algebra classes all across the planet are obsessed with the letter X. If you don't know what a number is, call it X. All right. So as a link to algebra classes, I'll call this an X1 machine. But you do know dots here are always worth 1. And you know X of these, whatever X is, will make one of those. This is also worth X1s. And you know X of these, whatever they are, will make one of those. This is worth XX's. X group of X, that's multiplication. X times X, X squared. And X squareds makes one of these. And XX cubes makes one of those, and so on. So there is a general machine. Now, for example, if I tell you X really is 10 in my head right now, then this would be a 10-1 machine. 1, 10, 10 squared, 100, yes. 10 cubed, yes, 1,000. 10 to the 4th, 10,000. Yes, that's correct for a 10-1 machine. Well, I told you X was 2 in my brain. Then it would be 1, 2, 2 squared, 4, 8, 16. That would be a 2-1 machine. Here's what I was required to teach my students as a high school teacher. Please divide these polynomials. Please divide something like 2x squared plus 7x plus 6 by x plus 2. And suddenly you panic. You say, whoa, James, you just did grade 5 mathematics, and now you want me to do year 11, year 12 mathematics? And the answer is yes, because guess what? We can do it. We can do it. I can draw a picture of 2x squared, 7x plus 6. 2x squareds, there they are. 7x's, here they are. And 6-1s, there they are. Here's a high school algebra problem. Please look for groups of x plus 2. What does that look like? 1 dot and 2 dots. Whoa, okay. Do you see any 1 dot next to 2 dots? Why? Yes, right there. 1 right there. All the dots must be there and kaboom, spilled over. Do you see 1 dot next to 2 dots? Yes, another one right there. Excuse me. Another 1 dot next to 2 dots. Right there. Another 1 dot next to 2 dots. Right there. Another 1 dot next to 2 dots. Right there. In fact, I'm seeing 2 at the x level, 3 at the 1's level. The answer must be 2 x's and 3 1's. Here's the thing. Look at this. I bet that felt like deja vu. I feel like we've been there today already. Because look at this grade 5 problem we did. 276 divided by 12 was 23. Look at the pictures. Look at the pictures. They are identical. They're absolutely identical. In fact, if I told you x really was 10 in my head all along, what number is this? This would be 2 times 10 squared, 100, plus 7 times 10, plus 6. That's 276. Divided by 10 plus 2, divided by 12, equals 23. Of course it is. Of course it is. I wanted my high school students to know, first of all, the human story of place value and how powerful place value is, and how all the elementary school teachers had set them up beautifully. Doing this work in elementary school is really all of high school algebra as well. And even as a university professor, I know this is just the beginning of the story. It goes further and further and further. So I'm going to stop there. There is the taste of exploding dots, just the beginning of a wondrous human story. Thank you so much for letting me prattle on for 55 minutes about this joyous subject. And I'm happy to keep talking about it because I love it so much. Thank you, everyone.
Yeah.
Stop sharing my screen.
Okay, thank you. Muchas gracias, James. Ha sido increíble, la verdad.
Thank you, James. That was amazing. We could just keep talking about this. The teachers have seen you, doing division with polynomials, and they're just absolutely amazed. And as you say, it's just the beginning of a long journey. Yeah, no, your head explodes too. Yeah, absolutely. So it's just the beginning of the journey, as we were saying. So you learn the rules well, and then you just keep going. It's amazing. So we have a question. We have several questions, and we're hoping to drum up more. But there's a question from Israel.
Si las calculadoras o los ordenadores calculan de esta manera, como si los ordenadores utilizan esta manera de calcular o cómo funcionan. A ellos le interesa. ¿Me oyes?
Can you hear me? Can you hear me? The question, oh, sorry. The question is this how computers compute?
Well, yes. Computers only have, if you like, two fingers. Well, basically one finger can either be on or off. So absolutely. So we did the X1 machine, which is universal. That's how everyone computes in all languages. Make X equals 10, and that's going to be how we humans do computing. But if you make X equals 2, this is a 2-1 machine. All the numbers are going to be expressed in terms of ones and zeros. So yes, computers actually do compute like this. They really do. And one thing I didn't talk about today is about issues of negative numbers and subtraction and so forth. But actually, even in this sort of system, negative numbers and subtraction is a natural place, and computers use ones and zeros for negative numbers as well. So on the next chapter of the story, we should also talk about all the negative numbers that I skipped over today, because it keeps unfolding. So yes, computers do compute this way. By the way, I should point out, people are working on optic computers that use polarized light. So our electrical switches are either on or off, but with polarized light, they can have light that comes in at one plane, light that comes in at an orthogonal plane, or you have no light, which means they suddenly got 3 symbols. So computer science would go from using 2 symbols, ones and zeros, to using 3 symbols, 0, 1, and 2, in which case they will do everything in base 3. And that actually is going to store much more information, and that can actually be much faster computers. And of course, there's also things like quantum computing, which is going to wipe out everything if they ever figure that out. But you know, if they ever use polarized light for computers, then we'll suddenly go from base 2 to base 3 and have even more powerful computers. So actually, if you think about all bases at once, you are thinking about all possibilities that could happen in humankind's future as we use our technology. You'll love it.
Sí, es maravilloso. Es lo que decía al principio, que es genial porque sirve muy bien para entender.
Yes, as I was saying at the beginning, it's really wonderful because it helps understand the basis of computing, which is an iterative process. Because you're learning math this way, you're also learning how computers work. And by the way, base 3 is really interesting. And of course, quantum computers, well, those are the future, aren't they? Do we have any more questions from the participants?
De la audiencia. Si no, lo que podemos hacer es
questions from the audience. Otherwise, for now, what I can do is introduce Carmen Casares and Sergio Belmonte, whom I mentioned earlier. Carmen Casares is a physicist, a mathematician, and a high school teacher in Madrid. Can you remind me of the name of your high school? Juan de la Cierva. High School Juan de la Cierva. Oh, that's right. The other day we were joking about that. Juan de la Cierva was the inventor of, well, a Spanish version of the helicopter. So anyway, Carmen is going to tell us about how this can fit into the math curriculum, which is something high school and grade school teachers worry about. And then we'll hear from Sergio Belmonte, who is the vice chair of the Math Museum of Catalonia. He can tell us, I mean, he's a high school teacher, but he can also tell us about how he uses exploding dots to teach grade school teachers. So, oh, I just saw a question. I just spotted a question that just came in. So that way, Carmen, you can get ready. James. Do you think exploding dots is a good approach for students who have trouble learning math? And do you have any specific experience working with special needs students?
So the answer is yes, of course, it's worth giving it a try. Any approach that can reach out to students in mathematical thinking in different ways, is worth pursuing, and maybe it will click. This Exploding Dots story has now reached 6.5 million students and teachers across the planet of all backgrounds, all abilities, and we've got lots of anecdotal evidence, at least, of great success. Even with students who have dyscalculia, how do you say that? They have trouble thinking through numbers. The visual approach, making this extraordinarily visual, has helped tremendously. You'll find things like, I was making it in the story, that 2 dots would explode, kaboom, become 1 dot, one place to the left. And people worried for a while that I don't make the dots bigger. Well, if it's 2 dots, they should be like a bigger dot that's double the size. And some students do have trouble with that, and it's worth talking about. And the reason we don't double the size is when I write a number like 777, that 7 is 7, that 7 is 70, it should be 10 times as big. That 7 is 700, should be 10 times as big again. We don't write numbers like this on our page in everyday life. So it's worth having discussions like that. We don't write numbers like that in everyday life. So my dots aren't going to be bigger as well. But there are going to be those moments. But the visual approach of exploding dots has proven to be tremendously successful, at least from the stories we're hearing and the observations we've made. It'd be a lot if someone did an official research study on the impact of learning on exploding dots. I'm not a math ed researcher. I invite anyone to come along and give it a try. That would be fabulous to actually get some empirical evidence as well, not just anecdotal.
Okay, great. Okay, so if you want, si quieres, Carmen, puedes empezar.
Okay, so then, Carmen, you can now kick off with the fitting into the curriculum, which has a lot to do with that question we just tackled, right? Okay, so I'd like to start by greeting everybody. Good afternoon. Before I start talking about how this fits into the curriculum, I wanted to thank everyone who has made this possible. Fundación La Caixa, the educational section, which is EduCaixa, and you who represented Marta. So we'd like to thank you for giving us this opportunity to spread the word about this amazing project. I'd also like to thank Fernando Blasco of the Royal Society for Math. And of course, we especially are grateful to James for creating this system and for showing it to us too, joining us here today. So before we go into going into how this fits into the curriculum, I did want to thank everybody. Now I'm going to share my screen because sometimes a picture is worth a lot more than 1,000 words. So I'll just go straight into sharing my screen. Let's see. And I'll discuss how this project fits into our education system, our curriculum.
Bien, pues disculpad porque tarda un poquito en cargarse la primera imagen, sobre todo porque es dinámica.
I apologize. The first picture is a video, well, or a moving picture anyway, so it takes a bit longer to load. The rest should load faster. So, before I talk about how this fits into the framework, I'll just go over what James has just told us, although he's done it in a much more communicative way. Okay, so these are the contents that have currently been worked on the most, for the classroom context using exploding dots. We've got 9 different levels shown here with different kinds of content. These 9 levels are 9 experiences that are already, pre-designed for you with your student handouts, with your teaching guides, and even games, specific games in a web app. These are the main themes, but they're not the only ones. You can move further, you can investigate further applications way beyond this, but in any case, we'll focus on these because these have already been developed for the classroom setting. The contents that James described are for levels 1, 2, and 3. He's also introduced he didn't mention anti-points, but he did introduce division and polynomials, so 5 and 6. And you can go to infinite sums and decimals and strange machines or weird machines. So these lessons are developed, as I said, in different platforms and different projects, including the one Marta described at the outset, Global Math Project. So we have 3 levels. We have guidelines and handouts, teaching guides and handouts, we have videos, and we have the web app. The student guides and handouts, well, the handouts have been translated into Spanish, and the videos and the web app have also been translated, so you can work with them directly in the classroom. The other nice thing about this amazing set of resources, I'm telling you about the resources so that you know what you can do in the classroom. The great thing is that they can fit into whatever technological setup you have in your school. If we have a highly technological school, you can use the web app with the different levels and islands, so the kids just play and they face and meet the different challenges. If we don't have computers available in the classroom on a daily basis, we can use the videos and the handouts and teaching guides. And if we don't have access to a video, we can just work on paper. And of course, with also hands-on materials like James just did, using counters, using dots, balls, whatever, anything that you can handle with your hands, because that is really important. So how does this all fit into our education system? In order to set the framework, I'll be referring to Spain-wide legislation, because in Spain, every region is responsible for education, and it kind of fleshes out the criteria and standards and so on and so forth. But there are general standards which are set in royal decrees, as they're called. That's the name of the legislation, for primary school and early secondary school and the last 2 years of high school. In primary school and high school, all the contents and assessment are done on the basis of 5 major blocks. You can see the ones for primary school on the left and the ones for high school on the right. So depending on where we're teaching, I'm sure we'll be able to recognize which blocks are ours. So if we take these 5 blocks, exploding dots works on the ones shown here. Mathematical processes, methods, and attitudes. This is a cross-cutting part of the curriculum. This is a hands-on system, and it works with every kind of content we have in the education. And as James pointed out, the second block, which is numbers for primary school, numbers and algebra in high school, well, that tallies perfectly with the exploding dots machines. But we can also go further. We can augment the methods and machines and apply them to other kinds of content that might seem a little less obvious. In primary school, we can use them to study measurements. You can use the 10-1 machine to study the decimal system and learn the decimal system easily. And if you use boxes and balls to invent a 61 machine, you can do time conversions. And in high school, you can work on functions and analysis using the same approach. You can also use dots to work on sequences and limits. And so that's the analytical part of math, and so on and so forth. And I'm sure we could come up with a lot of options going beyond these, the exploding dots and the machines that explode them. So here we have more or less what the contents are that are covered in each grade. This is a timeline, which is just an approximate timeline, a suggestion. We know that each region in Spain fleshes out the curriculum, and each class also determines what we can teach and when we can teach it. And in reference to the question asked earlier, each individual student can be a conditioning factor. For some students, we can work with very advanced machines or complex machines. With others, you have to just keep working with the more basic machines, and just reminding them of the positional system. So James has covered a lot of this in his presentation, but if you look at the experiences and islands that you have in the teaching materials, you go further into a lot of the options. Note that some of the machines come up again in high school. You learn about bases at the earlier levels. You can see certain islands for experiences. Oh, you can see which island appears in which experience. So these appear in experience 1, 2, and 3. Subtraction, multiplication, experience 3 and 4. But in experience 8, which seems to be more high school oriented, well, experience 8 can also be used when you're introducing decimals, the decimal point. And then, aside from that, you have the contents developed. You have the possibility of using the machines for anything that we might come up with ourselves. In fact, sometimes you don't need to fit them into a rigid curriculum. You can just play with them during those times of the year when you're meant to be having fun with math without actually, moving further in the curriculum. So this is something that you can do. It's a very interesting and hands-on way of working on math. Here we have another piece of legislation that is also in force everywhere in Spain. It stipulates how to select and use teaching materials, which is an essential part of teaching methods. That's what it says. It's an essential part of teaching methods to select and use teaching resources. Well, exploding dots fits in perfectly here, because we've always taught algorithms. We've always taught the positional system. What does this method contribute to education? In primary school, I think you're much more used to applying constructive, hands-on methods. We in high school are a little less used to that, but it's a good idea for us to get used to it, because this enables our students to connect and build on ideas that they already know. They're used to working with normal numbers, and then every time they encounter a new machine, they can figure out where it will take them. If we see that the student is not following the explanation, we can provide an explanation. And this is where our role as teachers comes into play. We can help them discover things that they may have trouble discovering on their own. And then, of course, once they've learned to use the machines, they can apply them to different kinds of learning. And, so this fits in with everything that has been said by authors about the psychology of learning. Anyway, we could talk and talk and talk about this for ages, as James pointed out. This system uses learning through discovery. It develops the ability to observe and notice things. It even develops reading comprehension. It's also a very motivational way of learning because it uses play, and it also addresses diversity in the classroom, diverse students. And so it, again, it fits in with the curriculum in another aspect. Exploding dots help develop a lot of the skills that are described by our national curricula on, mathematical skills, digital skills, learning to learn, and enterprising approach and proactive approach. But especially, above all, what Exploding Dots does is develop a taste for math, which is something we all think is very, very important to pass on. So, okay, that's it from me for now. Thank you very much, everyone. I hope you're as excited about these machines as we are. I hope you can start using them in the classroom if you haven't done so already. Thank you very much. Marta's microphone isn't on.
No te oímos, Marta.
Marta, we can't hear you. Oh, I was just saying, can you hear me now? Sorry about that. Yeah. So, no, I was just saying, wow, what a lot of work you've done. What an amazing discussion of how this fits into the grade school and high school curriculum. I think we're going to record this and put it down and put it in writing for the teachers, because you clearly show that you know Exploding Dots very well and our educational system very well too. Even from the perspective of legislation. So thank you so much. We will now go over to Sergio. We hope to leave some time at the end for questions. But there are some questions from the audience now that are about how to start working on this. Other questions are about concepts. We'll try to pass those on to James. But the ones about using this in the classroom are the questions I'll hand to Sergio so that you can take them or include them in what you cover. Sergio. One of the teachers was asking whether the Exploding Dots method can be used, or whether you're using it as an alternative to what your daily teaching is, or whether you're using it as your central way of teaching math. Another question by somebody named Olivares is, what is the advantage of this compared to, say, an abacus or multi-links or other representational systems that involve, object manipulation? Well, thank you very much. First of all, I'll say it's a pleasure to be here with James, Marta, and Carmen, surrounded by very talented people. I'm going to tell you about my own experience using Exploding Dots and how I've used them in the classroom, and then I'll answer your questions because it all fits in together, doesn't it? I'll start with a story that I'm sure you will all recognize. I started teaching math. I'm a mathematician. I'm a high school teacher. I started out 17 years ago or so, and I'll always remember my first class. It was a 10th grade class, and I had to teach polynomials. I'm a mathematician. I love polynomials. I'm mad about polynomials. I'm fascinated by them. And I was telling them about polynomials, and I was just, Ruffini's decomposition, you name it, loving it. And so at the end, I said, as usual, do you have any questions, kids? And they asked me a question that math teachers always get. Somebody raised their hand and said, hey, teach. What's this for? Right? Used to that, huh? I was inexpert. I was a rookie, very young. And I was like, oh, polynomials. Well, I mean, polynomials. And I said, hey, do you want to pass your secondary school diploma? Yeah, well, you got to learn your polynomials. And of course, that was frustrating because I wasn't awakening curiosity. I wasn't sparking curiosity. So ever since then, I was looking for ways of sparking curiosity, because curiosity is the straightest way to achieve learning, especially in this case of math. So when in 2017 I discovered exploding dots, I believe that was the year James launched exploding dots to the world. And I saw a tweet by James, exploding dots, Global Math Week. I was like, what? Exploding math? That can't be. And when I studied the system, I said, oh, this is amazing. And I took it into my classroom. Let me tell you how I brought it into the classroom and what I achieved. That's, in a way, an answer to your questions. I took it into the classroom at the outset in these, time off hours, in 10th grade and 11th grade, but as a kind of an extra. But of course, in high school, especially the last 2 years, we're really college entrance exam oriented, so that's, just before the holidays, that would be a good time to fit it in, those sort of crazy teaching hours. And the kids loved it, and they wanted to learn more. The first time I used it was during a class hour that was just before recession, and the bell rang for recession, and the kids wanted to stay and they wanted to learn more. So, recess. Yeah. So the one thing is that, exploding dots trigger curiosity and spark an eagerness to learn. They don't ask what exploding dots are for. I mean, what's the point of exploding dots? Oh, who knows? Same as polynomials, perhaps. But what about the pleasure of just getting stuff to explode? And that's when they want to learn more. That's where the innate curiosity about math is awakened. And then there's the potential for self-learning too. There's all sorts of materials, and they can keep learning stuff on their own with all sorts of materials if they choose to. I also gave them the opportunity to tell others about it, because the interesting thing here is that when you get all excited about something, you want to share it. And it's really important to give students the space to share their discoveries and their happiness about these discoveries with others. So I gave them space and opportunities to tell other students about what they've discovered. So this ties in with the question asked earlier, what about students who tend to lag behind the rest? How do you hook them? Well, you get their classmates to hook them, because their classmates have enjoyed their discoveries. So my first experience was in 2017, and then I started using them in 7th grade. I mean, a lot of these students have learned most of the basic exploding dots content in primary school, so it was hard to fit into the curriculum up to a point. But, if you look at integers, when you're learning integers, I taught integers using exploding dots because, typically you teach integers with elevators and all sorts of weird things. Well, in the case of exploding dots, you use dots and anti-dots. So I started doing this in 7th grade. Now, once you leave the door open for exploding dots, I mean, there's a feedback loop and it just snowballs. So then I was using it almost exclusively in optional math subjects. I mean, I devoted a whole quarter to exploding dots in optional math subjects, whether they were 7th grade or 8th grade math. If they were optional, I just went for it, and I got as far as I could get without caring. Now, primary school, grade school teachers finally are amazed because they can finally get kids to finally understand why they have to carry one, and they finally understand why they have to carry one, and they see how they can teach their students. So I suggest that you put this to teachers or students, that, the idea of teaching somebody else about exploding dots, somebody who's not doing math, who they're not doing math with, their father, their brother or sister, their dog, you name it. So I suggested that teachers teach somebody else how to use exploding dots and record it and send the video to me. And they were all amazed to see how amazed the person learning from them was and how the person was getting it. And what are the advantages of this method compared to others, such as using an abacus or other, well, hands-on materials, object manipulation materials? The thing is that algorithms here become quite visual, and this is a higher level of learning. Anything that you can grasp both visually and on an abstract level just takes on a different dimension. I mean, ever since I saw all this explosion happening, I can't see a polynomial without seeing explosions. An abacus is a bit more abstract. I mean, if you work with it properly, it might add up to the same. Other kinds of object manipulation systems may be very helpful, but something like an explosion is just amazing. I work a lot with object manipulation, and this is complementary to the rest. I'm not saying it replaces everything else, but it's really, really worth trying. Just let your students try this and ask them questions. I mean, here's another spoiler. What if we build very weird machines? What about a 3-2 machine? Can you imagine what a 3-2 machine could be? What is that? Oh, and wait a minute. What about a 60-0 machine? Does such a thing exist? Oh, and wait a minute. Listen, what about a 1-2 machine? Huh? What if we reverse that? Can we do that? Well, anyway, I'll shut up now. That's it from me. Okay, well, you're allowed to shut up as long as we keep going somewhere, sometime. Okay, we've sown a seed. We've planted a seed. That's it. Okay, well, thank you very much. But it's 1 minute past 8. We have to wind up now. Thank you very much. I mean, I just hope this is just the beginning of a long journey for us. We'll keep doing this sort of thing, and we'll keep organizing education for teachers, high school and grade school, how you can work with weird machines, as Sergio just mentioned, using exploding dots for analysis, as Carmen described. There's one more question I have to put to James. Thank you, by the way, all of you. It's been spectacular. It's been amazing. I think this is an amazing resource for teachers from every point of view. As all three of you have mentioned, what really matters here is developing a taste for math. And you develop a taste for math when you understand the rules, and exploding dots help you understand the rules. So thank you very much. James, here's a question for you. I don't think there's much time for you to answer, but I promise I'll place your answer somewhere visible. What about negative coefficients and polynomials? We won't have time to cover that now.
Well,
Anyway,
absolutely. That's the fundamental question. You are such a mathematician. You are thinking like a mathematician. There's a natural next question. What about negative coefficients? How sneaky of me not to give an example of one today. So that's going to open up another portal of wonder and exploration and delight for you. How would you possibly handle negative coefficients? So what is x squared minus 1 divided by x plus 1? I know what the answer is meant to be as a high school teacher, but how could you possibly see it in exploding dots? Is there a way? And of course, the answer is yes, there's always a way. So go for it, explore, play with the wonder, play with the delight, play with the awe that is mathematics. And I have to say, thank you everyone here for organizing this incredible session. And thank you for just bringing the joy of math, just setting math free to be joyous amongst all our fabulous students. They are our next generation. Let them go forward with intellectual play and wonder and awe and joy and all the tools of mathematics, both the intellectual power and the intellectual joy. So thank you for promoting joy across your beautiful, beautiful country. Thank you so much, everyone.
Ok, tenéis en el link, ahora os pondremos la página web del Global.
Okay, in the link we will also, we'll be adding the link to the Global Math Project, where you'll find all of the materials. And in the page where you registered for this, you will also find links to the earliest chapters, where you have handouts too. And you can be part of the Global Math Project. I think that's it for me now. I'd like to thank James and Sergio and Carmen, as well as Fernando Blasco, who has really helped us. I'd also like to thank Marta and the Royal Spanish Society for Math. And well, that's it now. And just follow us, be aware of us, because by the way, this has a lot to do with math and computation. And I'll just leave it up to James on his own to say goodbye, because I don't want to be the one to say goodbye.
Farewell, one and all. Here's to the joy of mathematics, and thanks for being great ambassadors to awe and wonder. It's a human story. It's a beautiful creation of humans. Let's share it with our wonderful human students. Thank you, one and all.
Thank you. Vale.